Humanity has always imagined a way to cross the sea without being defeated by storms, distance, or the darkness below. Bridges have risen above oceans. Real undersea tunnels have already proven that people can dig through rock, clay, and pressure to connect lands once separated by water. But what if an undersea journey did not have to feel hidden, dark, or silent? What if traveling beneath the ocean could become a breathtaking experience? A voyage through a transparent world where passengers move safely inside a tunnel while the living sea surrounds them. This video explores that bold vision, a half-real, half-futuristic undersea transport concept set in Japan, a country known for precision engineering, coastal megaprojects, earthquake-aware design, and the ability to build in some of the world's most challenging environments. This is not a real existing project, but a creative engineering fantasy built on believable technical logic. It combines reinforced concrete tunnel sections, pressure-resistant curved glass, steel titanium support structures, emergency flood doors, underwater maintenance robots, modern rail systems, and transparent observation chambers that feel like a giant aquarium beneath the seabed. The journey begins at both ends of the route. On one side, a mainland coastal construction site rises near the shore. On the other, a colder northern island-side portal prepares to receive the tunnel. Before any machine can dig, before any glass tube can be lowered into the ocean, engineers must answer the most important questions. Where is the seabed stable enough? How strong are the currents? What layers of rock, clay, and sediment lie beneath the water? Can the ocean floor carry the weight of a structure that must resist pressure every second of its life? Survey vessels, sonar scanners, floating buoys, seabed sensors, geotechnical drilling rigs, and remotely operated underwater vehicles begin the first stage of the story. They map the hidden landscape under the waves, measuring depth, slope, current, and soil behavior. The future tunnel is still invisible, but its path is slowly being drawn across the seabed through data, markers, and careful engineering judgment. Then the landside construction begins. Temporary roads, storage yards, material zones, cranes, power stations, drainage systems, and control facilities appear along the coast. From the surface, reinforced concrete approach tunnels are excavated downward toward the sea. These early sections are the most realistic part of the project. Strong, dark, technical passages supported by concrete lining, steel reinforcement, waterproof membranes, rock bolts, ventilation ducts, drainage channels, and emergency systems. They are not spectacular yet, but they are essential. They form the safe backbone that connects land infrastructure to the futuristic transparent section under the ocean. The most extraordinary part of the concept is built separately in coastal fabrication facilities. Long cylindrical, transparent tunnel modules. These modules are not simple glass boxes. They are engineered as round tube segments because a circular cross-section distributes water pressure more evenly than a rectangular shape. Each module is formed from repeated circular steel titanium rings, longitudinal titanium ribs, curved multi-layer pressure-resistant glass panels, waterproof polymer gaskets, circular end flanges, and protective sealing systems. This technical logic is what makes the fantasy believable. The transparent section may feel like science fiction, but it is not treated like magic. It is imagined as a future evolution of marine engineering. Stronger materials, smarter sensors, deeper pressure testing, and modular construction methods. Inside the fabrication hall, titanium rings are machined, inspected, coated, and assembled into circular frames. Curved glass panels are lifted by suction rigs and inserted into the ring grooves one by one. Each panel follows the same cylindrical geometry, slowly closing the round tube wall. Waterproof seals are compressed along the edges. Secondary anti-leak gel is applied around every glass to titanium seam. Circular end flanges are attached so that each tube segment can later connect to the next. Before a module ever touches the sea, it must survive pressure testing. The completed cylindrical glass and titanium tube is placed into a curved cradle shaped to support its round body. Pumps, sensors, test hoses, and inspection devices simulate deep ocean conditions. Engineers check for leaks, deformation, seal weakness, flange movement, and glass stress. Only after passing inspection can the module be transferred to a marine transport cradle and moved toward the dock. Offshore, the project becomes even more dramatic. Floating cranes, barges, survey boats, and underwater robots gather above the route. On the seabed below, anchor bases have already been prepared and protected by anti-scour rock. The first cylindrical transparent module is slowly lowered from the barge through the blue water. ROVs guide it with lights and robotic arms. The round tube hovers above its foundation, aligns with locking grooves, and descends until its support shoes settle into place. Hydraulic clamps secure it to the anchor bases. Crane cables are released only after the module is stable. Then the process repeats. Another cylindrical module is lowered. Its circular flange is aligned with the first module. Waterproof gasket rings are compressed between the two sections. The joint is sealed, pressure tested, scanned, and verified. One by one, the transparent tube segments form a continuous undersea corridor. From the outside, the structure looks like a glowing blue line running along the seabed. From the inside, it will one day feel like a passage through the ocean itself. But before passengers can enter, the tunnel must become a complete transport system. Emergency flood doors are installed at both transition zones, between the concrete tunnels and the transparent modules. Drainage channels and sump pumps are connected. Power conduits, communication cables, ventilation ducts, monitoring cameras, leak sensors,